Um, Hello everyone, my name is Zbigniew Skowron, and today I will be talking about simplifying control flow. So we have many different code complexity metrics that tell us how easy our code is to understand, how easy it's to change. So the first one is number of lines of code. So this is straightforward. Yeah, so the other one we can talk about is nesting depth of code in our functions. So in the example, we have a function that is calculating whether a year is a leap year or not. And it's really badly written, as we will see, because there are many nesting levels, and it's very difficult to understand what's going on. Because if we take any line of code, for example, the first one that's highlighted, we have a very complex context of the conditions of the previous ifs that determine, under what circumstances given line of code is executed. And then if we go from this line of code to a line below that, we see that we have to mentally pop some context from some ifs and then push another context with different condition and negate it because it's an else branch. So actually we have huge problem in dealing with this mental model we have if we have deep nesting. So another metric is branch coverage, which basically counts how many runs we have to do to exercise every possible branch in our code. So this is the lowest number of tests we need to test a function, but not necessarily sufficient. It's a theoretical lowest limit. So another metric is total number of all possible code paths through our code. And yeah, it gets big, and most of the time it's infinite, right? Our functions can have loops that can have arbitrary numbers of iterations, so we will have a lot of code paths. And to test a function fully, we would have to check all of those, which is impractical. Yeah, so we have another metric, which is cyclomatic complexity, and it basically measures, this is something in between of the branch coverage paths and all the possible paths. It's a very conservative compromise between those two. So it basically says that ifs and loops complicate our code and make it harder to reason about, harder to analyze, harder to test. But on the other hand, returns make our code simpler, because if we have a return, then we know that this particular path will not diverge into many other paths in the future, because it ends right here. So it simplifies our code. So in this example here, we have some number of if statements. And we see that the total number of possible paths through this first function has exponential number, it's exponential with the number of ifs we have. So it is still possible to reason about this code and say whether it's correct or not, but it's difficult. And it gets more difficult, if in our function we actually do something useful. On the other hand, if every if ends with a return, then the number of paths through our code is linear, so it's really manageable. So returns are good, returns are our friend when we want to reduce complexity. So we don't like nesting, we don't like ifs, and we don't like nested ifs, but we do like returns. So a small guideline. Do not put an else after a return, a throw, a break, continue, because it is always confusing for the readers. So on the right side, we have code that have a return in an if and then an else, and then some code after that. So the question is, if the left-hand code is identical to the right-hand code, equivalent, then so what's the difference? Was there some oversight? Maybe someone was thinking he's writing proper code, but it was a mistake. Maybe he overlooked the return, and the do more function was supposed to be called in both branches. So it raises questions, and it's confusing for the reader. So don't do that if you want simpler code. So if we will apply this one simple rule, we take the code on the right to look, on the left to look like the one on the right, which is slightly better. It's still bad, but it's slightly better. We have a little bit easier to understand it. So a little guideline number 2, it's something that our IDEs already can do for us. So invert conditions to reduce nesting. And if we take the code on the left and invert conditions appropriately to reduce the nesting of the if statements, we see that we end up with very simple and very clean code. So the guideline is write linear code, which means that every if statement ends with either a return or a throw or break or continue. So when we write like this, we often get rid of nesting that is unnecessary, conditions that are necessary, and state in functions that is unnecessary, like this lib variable in the example. So inside loops, like I said, we can also use breaks and continues. They are also simplifying our code inside loops and make it easier to reason about. So what are the benefits of actually writing the code this way? Well, first of all, function written like this can be written from top to bottom in one go, and we can understand what it is doing in just one go without backtracking, without needing to switch our context from one if to the other, without complex mental exercises when we try to go from a positive branch to an else branch and also an else branch in another if on the outside. So basically, it's much easier to build this mental model in our heads, and we can do it basically most of the time in one reading from top to bottom of the function. And also we get much fewer possible code paths. Like we get linear number of code paths, and all of those look exactly the same. They go straight down and then exit, and then straight down and exit. So it's very simple. And what's functions written this way, how do they look? Well, they have very clear structure. First of all the parameter validation just checks the parameters and exits, and we're done. So we now know we have simpler context below that. And after that, we take easy cases, and we just return the value, and we're done. So now we handle corner cases. So those difficult cases, those tricky cases, and we just handle them and get out. And what we're left out is something very simple, very clean, where we can simply just return the value that is the common case and get out from the function. So our function is not only easier to read and easier to reason about and test, but also with each if down the function, we have simpler context to work with, because we get rid of those special cases and get simpler and simpler context. So the question is it even possible to write code this way? And it actually is not only possible, but quite easy. And it turns out that parts where there is some difficulty are usually parts where we see that some code should really be a helper method. So we extract it, and we have cleaner code, more modular, and better. Another case is where something should really be a standard algorithm. So we apply the standard algorithm, and the code is cleaner, easier to maintain. Another situations where we have difficulty writing function this way is simply when our function is just too complex, or written badly, or there is just some code that doesn't make sense. It's also quite often. So actually this process of writing code this way helps us build code that is simpler, that is more logical, better structured, and separated into logical pieces. So here's a code before applying this rule, and we have like nesting galore. We have 3 nested for loops, lots of ifs, and it's terrible. And after applying those rules, we have much simpler code. First of all, we have only 1 for loop left, right? There were 3 before. So 1 for loop, it turned out it was completely unnecessary. It wasn't doing anything. It wasn't easy to see in the original code, but if we simplify, we see that it was simply redundant. Another for loop was changed into a standard algorithm. And lots of code was deleted because it simply served no purpose. It was just occluding the real real meat of the function. So some people would argue there is still 1 for loop too many in this function, but it's definitely better than what was previously, right? So yeah, another thing to talk about are loops. So there are 2 kinds of loops. There are loops that are trivial, which are usually for loops over some range. And there are loops that are not trivial. And those are usually while loops, not necessarily always, but usually. And how do we write them? Well, we start with writing while, and then we write open parentheses, and then we put exit conditions there. And this is a big mistake, because exit conditions written this way usually will complicate the code inside the loop, the code after the loop and before the loop, and will be very difficult to analyze because they will be too complex. So actually what we should do is to write while true loops. So infinite loop. This is the beginning and usually the end of any loop that should be complex. So inside a loop like this, we write linear code. Every if ends with a break, return, continue, or a throw. And it turns out that our exit conditions come out naturally. The code is simpler. Between exit conditions, we have some useful code that makes the flow clearer. And it's much easier to verify that our exit conditions are actually reasonable. So here is a loop written like this, and it would be much more complex if we would have exit conditions in the while statement. So another thing I like to point out is that we should avoid writing do-while loops, because simply people have troubles of comprehending how it works. And most often exit conditions in do-while loops are simply wrong. And even if they are not wrong, the next person that will read this code will probably misinterpret this exit condition and misinterpret what the function is actually doing. So just try to avoid the while loops. If only you can use while loops instead. So you can also use local functions if you want to extract some function, but don't want to make a separate one. Just use a local lambda, which works great. So Thank you very much. Just remember to write linear code and write loops that start with while true, and your code will be much simpler. Thank you very much.